Thank you. Once again, thank you for inviting me. I really appreciate the opportunity to basically give you an idea of what my research program is. And I especially appreciate the opportunity to again see Steve again. We have had a fruitful collaboration for the last few years. It's been one of the most exciting intellectual ventures that I've sort of gone on. So with that, I want to basically talk about one core program in my research career, and that's to understand the fundamental limits that govern the construction of secure protocols. And so in order to do things efficiently, in order to do things better, you really have to understand the limitations, where you hit bottlenecks. And so in this talk, I want to sort of try to give you two bottlenecks that we've encountered and figured out ways to get around them. And of course, this is an ongoing research program as to find other ones and so forth. In order to start that, let me first give you a brief synopsis of how typically secure protocols are constructed today. So typically we start with some simple protocol, and then what we do is we apply a systematic transformation to every step of that simple protocol in order to make a more secure protocol. Okay? So it's a security transformation. That this is how we reason about security. We basically take some simple task and then we systematically transform it. Just like the way we build programs is we write something and we have a compiler which systematically transforms a high-level description into a program description. So let me give you two examples of this process, one highly successful and one not so. Okay? So the very successful one is like a simple protocol for interacting with your bank as soon as the internet came along was this, let me do web banking. Let me do all the things I typically have to go to the bank to. Let me do that in the comfort of my home over this HTTP protocol and so forth. It was quickly realized in 1995 that this was not a good idea. People can eavesdrop on the internet and who knows what happens over there. So people created a systematic security transformation, which was what? Yes! So a very simple transformation, which is that every interaction I do with the bank, I wrap that around a secure channel like using SSL. Okay, and that was a very successful type of thing, and that's really created a billion, the $100 billion, sort of e-commerce market was sort of based on this security transformation. Now let me give you an example of a transformation that didn't work out so well, but was still guided by this principle. Okay, and in order to do that. Let's consider a protocol for robbing a bank. Okay, criminals have the same sort of mentality of, well, I would like to do this task of robbing a bank with a gun, but I understand if I do that just as it is, it wouldn't be very secure. I'd probably get caught. So probably have to do some sort of type of transformation in order to make this task a little bit more secure for myself. Okay, many people, many movies like Heist and all these type of things, basically investigate what this bizarre security transformation could be. Let me give you a real-world example, which I find highly interesting because it's so relevant and so sort of it gives such a parallel to what we sort of do, even in academia for trying to do this type of stuff. And basically, this Pennsylvanian named Mr. Wheeler, he had an approach, and let's basically investigate what his approach was. So he had walked into two Pittsburgh banks and he attempted to rob them in broad daylight with no disguise. Okay, and obviously this guy was caught because surveillance tapes show him in the act of doing this. Okay. When he was caught, he was actually in disbelief that he had been caught. And his explanation was, I wore the juice. Okay, so he was under the deeply misguided impression that rubbing one's face with lemon juice rendered it invisible to video cameras. And someone had basically told him this, and you might think as a child, if you write in lemon juice, it becomes invisible. So therefore, if you cover yourself with it, you also, make some metamaterial that makes, bends light around you and so forth. And so of course, this protocol was he had done this type of thing. He'd robbed the bank. He had the security transformation, robbed the bank with lemon juice and so forth. But it didn't really work out. Okay, and let me try to break down some of the reasons why. So this is a compelling example, and social psychologists have come up with other explanations for this type of behavior. But in my opinion, what happened was, first of all, he was using a heuristic security argument. It's something we also do in practice now. Okay. But although he was using a heuristic, so he didn't have any principle as to why, lemon juice would bend light to make him invisible to light and so forth. But he actually had experimental evidence to back up the fact that he was actually doing something secure. So when he was interviewed further, basically he said he had apparently snapped a Polaroid picture of himself with lemon juice on his face. And then when he developed that Polaroid picture, apparently he was not in that picture. Okay, so based on that sort of experiment, he thought that this thing would work. Okay, and you might wonder, how did he pull off taking a picture of himself and not having him show up? And you can come up with many alternative suggestions, like maybe the film was bad, maybe he had accidentally turned the camera that way while he's taking a picture of himself. He put it on the timer and he ran there and it took a picture before he got into it. Nonetheless, it didn't work out. And so essentially all of the overhead that he had put in the security transformation was completely ineffectual. And moreover, this overhead was very painful. As he indicates, basically the lemon juice was burning his face and his eyes, and he was having trouble in seeing and so forth, right? So this basically gets to, in a nutshell, if you remember this story, you remember the point of this talk, which is that we should really avoid the ineffectual type of overhead type of things, and we should really try to eliminate the painful overhead. So we really should figure out where the limits of what things we need to do to achieve security are, and just focus on those and try to get rid of all the other things that we do. Okay, and so let me give you a simple way to eliminate the first two type of things. So these heuristic security arguments and so forth. We've actually, since 1970, built a pretty rigorous theory that allows us to get beyond these type of arguments. So there's a systematic approach that we can use to convince skeptics, and people should always be skeptical about new systems. We have a rigorous way of convincing skeptics that a system actually works. Okay, and that system is based on this sort of theory of cryptography, this approach that you provide a mathematical security definition, you present a scheme and an assumption, and then you give a security proof as to why that scheme should really satisfy that definition under the assumption. Okay, and this, Steve, this is this essentially a security definition is a very mathematically rigorous statement which specifies exactly what is considered a break of a particular system. Okay, of course there's a trouble here in making sure that the experiment really captures all of the things that an adversary can do in an experiment to break your system, and that's a separate that's a different problem. But certainly one requisite is we should basically specify that, and then a security proof basically makes the following type of argument, which is to say, if you have some crypto system and some attack on the right over here that can break that crypto system, i.e. that can violate the definition that you proposed in the previous part, then what a security proof does is it allows you to take whatever this attack was, and the security proof itself is a transformation of that attack into some algorithm A, which solves a very hard problem, which violates your assumption. Okay, so like factoring, discrete log, one-way functions, structured permutations, you can make any of these hard problems, and the security proof takes the attack and transforms the attack into this algorithm, right? So this is a key idea. These transformations become very important, and in fact, coming up with the security proof itself requires many extra. In order for us to be able to come up with the proof, we have to what we found is we have to add overhead to these protocols. We have to add steps to them, which perhaps intuitively don't really do anything, but are necessary for us to make this type of security proof. Okay, and that's a consequence of this. On the plus side, that sort of paradigm to modern cryptography, it eliminates the concerns that you have from heuristic security. It also typically eliminates this overhead that's ineffectual. If you don't need something for the security proof, that's a really clear sign that you can remove this from your protocol, and so therefore you don't really do things that you don't necessarily have to do. Okay. But there's one thing left, and that's the rest of this talk. It's about the rest of these security transformations. Sometimes they're very painful. And these next two examples, I'm going to present basically a survey of two works, essentially, and they're going to discuss, how we, basically identified what the overhead was and how we basically overcame some of the problems with that. Okay. So what kind of overhead am I talking about? When you make the security transformation, you might add rounds to your protocol. So if before your protocol was just I send a message and I receive a message, after the transformation, it might be I have to send n messages and you have to receive n messages one after the other. That could be one. Another thing, you increase the amount of communication you have to do, or you increase the amount of computation that you have to do, or you require in your protocol, honesty. You require some fraction of the participants in the protocol to be honest. You can reason about some fraction that's not honest, but you require for the protocol to be secure some fraction of them to be honest. And in fact, all four of these things are things that I'm sort of investigating in this program. Today, I'm going to talk about these two, communication and computation. Okay? And again, the question is, what are the fundamental limits that govern, the construction of these protocols based on, what are the fundamental limits of communication and computation that govern these type of things, okay? And the problem that we're going to study is an important crypto result from the last century. And it's important because it's the most general, essentially. The result basically says that any collaborative task that you want to perform can be performed securely. Now I'm going to describe what I mean by collaborative task a little bit more formally later, but essentially it's if I have some input X and you have some input Y, by collaborative task, we basically want to compute some function f of x comma y. So it might be the case that we'd like to learn which of us is older. It might be the case that we are in an auction and we both have private bids on this wonderful statue, and we would like to run an auction such that we can determine which the winner is without revealing anything about our personal opinion about this wonderful sculpture. Okay, so I'm going to talk about for this general field called secure multi-party computation, or secure collaboration. I'm going to give two examples. One is a paper with my grad student Chi-Hao Shen, and it deals with the two-party case where there are only two participants, Alice and Bob. And the second case I'm going to talk about is the many-party case, and that's joint work with Steve and with my grad student Mona Sergi. And both of these papers are roughly from this year, but they started a little bit earlier. Okay, so for the two-party case, right, the important crypto result from the last century, from the 82 essentially, is that if Alice has some input X and Bob has some input Y, okay, any function that's polynomial time computable, any f that's in P essentially, there's a protocol which allows Alice to compute f of xy and Bob to compute f of xy, and nothing else. They don't learn anything else about x or y, just their input and their output. Okay? And before I can actually get to our results, I'm going to basically spend the next few minutes giving an overview of how this old protocol from 82 actually worked. And it works in two steps. It takes a simple protocol, and this is basically the step that Yao really focused on, okay? How to take a simple protocol and make it into one that I called honest but curious protocol. I'll explain what the security notion means, okay? And then you use general techniques, basically, to go from honest but curious protocols into fully secure protocols. And this is the step which actually takes the most overhead. And this is the step that our work actually addresses. But before I can explain what's going on in this step, I'm going to first give a synopsis of this part right here. Okay? So what does honest but curious security means? It means that the protocol is secure, meaning Alice nor Bob, their ability to learn anything that does not follow. So basically the definition says that breaking security means that Alice or Bob is able to learn, whatever that means, anything that does not follow from the input-output relationship of F, with the big caveat that both parties follow the protocol. So they're honest parties, they follow all the instructions, okay, but they're curious. They'll do anything they can in order to look at the transcript of their protocols and to learn something about Alice or Bob's input. Okay, that's the honest but curious part, also known as the semi-honest model. And obviously this is not something that we can run on the internet because we certainly can't assume everybody's honest, and we already know everybody's curious. So we really have to take this protocol and compile it into the malicious case to actually be useful in sort of the settings we envision. I have a definition here that I can go through, but I think if someone has questions at the end of the talk, I'll run through that definition, but I think I want to skip that part. Okay, so let me, as I said, I'm going to summarize the work that Yao did in 82 for going from a simple protocol to the honest but curious. So here's our collaborative task. What's the simple protocol? Okay, the one that we're going to start with. It's essentially as follows. Let's take F. And we know from general theory of computation, from basically the first introduction class, that I can take this function F and turn it into a circuit, right? Whatever programming language it's written in, I compile that into assembly, and I compile that into like circuits. And I have a bunch of AND and NOR and NAND gates and so forth that identify exactly what that function f is. So that's the first step that we assume that's been done. Take your function f, whatever task you want to do, and turn it into a Boolean circuit. And the simple protocol is, well, Alice and Bob can just put their wires, put their inputs right here, okay, and then just follow this circuit all the way up to the top to, basically learn the output. Okay, that's the simple protocol we're going to start with. And now we're going to systematically transform it into a protocol that's honest but curious secure. That's the transformation I'm just going to describe right now. So here's how it works. Right, so let's start with the circuit for F. And now the first key is, right, when I'm just evaluating the circuit, each wire has a what? It has a 0 in it or a 1, right? As I'm evaluating a circuit, the wire corresponds to either a 0 wire or a 1 wire. My first systematic step is that I'm going to attach two keys, two encryption keys to each wire. One key, the 0 key for each, so this is wire 0, wire 1, wire 2, wire 3, 4, 5, 6, wire 7, 8, 9, 10, okay? There are 10 wires in this circuit, and the output wire is off the screen. So for each wire, instead of having a 0 or a 1 there, I'm going to associate an encryption key, KI0, KI1, to that wire. Right? Does that make sense? Okay. And this key is going to have the following semantics. If I know this key, okay, that's basically, I'm not going to know whether the key represents a 0 or a 1, but the key is going to allow me to basically evaluate that wire as if it was a 0, okay? I'm jumping ahead though. The first step is for every wire in this circuit, create two random keys, KI0 and KI1, representing a 0 and a 1. Okay. And now the task is we want to design each gate so that it maps the input key to the corresponding output key. The task is, if I have the 0 key over here and the 0 key here, this gate is going to include information which allows me to compute the 0 key on the output. And similarly, if I have 0, 1 here, it's 0, and if I have 1, 1 here, it's 1. Like, in fact, we can make a table of this, okay? Let's make that table. So this is the information that's going to go in this little AND gate, and the task is, if I have a key here and a key here, this information should allow me to compute the correct key on the output. So here is a typical table for an AND gate. And by this you should know, you should observe that if you can do AND gate, you can do any gate that you want. Right? So 0, 0 goes to 0, 0, 1, 1, 0, I'll go to 0, 1, 1 goes to 1. So how might you imagine if you had the key for the 0 and the key for the 0, that you're able to compute the output key for the 0? Given that these are encryption keys. Steve doesn't get the answer. So the idea is they're encryption keys. So we're going to use encryption in order to basically encode this table. So let me give you an idea of how that works. So inside this gate, what I'm going to do is put 4 ciphertexts. Okay? And the first ciphertext is basically going to be a double encryption of the output key 0 using the first key, K01, and using the next key, K00. Okay? So I just encrypt the table in the natural way. Right? I just use the keys to encrypt what the output should be. Right? And what does this mean? This means if I have this key and that key, okay, I can basically decode exactly one row of this table. And that one row is going to give me the key for the output wire. This is why we call this a garbled circuit technique. And there's one little bug here. If I put this table exactly in this order, what's the problem? The what?
The order reveals the answer?
Exactly. So yeah, if I know that I had the third row, then basically I knew that the input on this side would correspond to 1 and the output, so forth, right? So what do? you permute the rows. Every gate you randomly permute in some random way. Okay? So this is what's called a garbled circuit. Each wire has a pair of keys. Each gate has this row of 4 encryptions. Okay? And notice if I have the keys corresponding to the input, I will be able to evaluate this circuit, and all I will learn, essentially, all the intermediate values are just random encryption keys. What I'll learn is basically the key on the output wire. And by convention, you could just make these keys right here 0 or 1 based on what the actual output is, right? So as a result, if I had the input keys, I would evaluate this, learn nothing about the intermediate representation because it was all just random keys. And at the output, I would basically get the fact that this is a 0 or this is a 1. Okay? So this basically leads us to the honest but curious protocol. Here's what Alice does. She makes one of these circuits. Okay? She picks the keys corresponding to her input because she knows the key, she knows the correspondence between the keys and the actual input bits. Okay? So she says, aha, my input's going to be 0, 1, 1. Whatever my inputs are x0, x4, and x8. So whatever those input bits are, those are the keys that I'm going to basically send. And I'm going to erase all the other intermediate values. Okay? And I'm going to send that over to Bob. Bob has a circuit and Alice's input. All Bob has to do now is get the keys corresponding to his own input, and then he could basically evaluate the circuit. All right? So how are we going to do that? This is the second piece of magic that comes into this protocol. The first piece of magic was this idea to garble a circuit, which is a really clever thing. But it's actually, once you see it, it's like you could have had this idea too, kind of, epiphany, right? So the second piece of information that you need is a way for Bob. Bob has his input bit Y1, okay? And if this is a 1, he needs to learn this key. And if it's a 0, he needs to learn this key. But the important thing is he needs to learn exactly the one that corresponds to his input bit. If he learns both, then he'll be able to learn more from the circuit because he'll be able to evaluate his circuit on both this 0 and 1. He could basically deduce some information about that. Okay, you can think about that. If Alice learns which key he learns, right? So Alice, he could say, here, here's my input Y1. Oh, here's the key you need, right? Then Alice would learn Bob's input. So neither of those trivial solutions work. And so what you actually need is a protocol called oblivious transfer. This was an idea that was really conceived by this guy, Stephen Weiner, in 1973. He was thinking about all sorts of quantum computation ideas that were sort of fomenting, like quantum coins, and he came up with this idea of oblivious transfer. You're basically thinking of, what's feasible with quantum devices that's not feasible with, normal devices. And then, 8-10 years later, this Michael Rabin basically came up with a protocol like this based on computational assumptions. And then since then, many people, like 15 people, have written papers on this. And so now they're quite efficient protocols for doing this type of oblivious transfer. And it has a simple property that this person inputs a bit, 0 or 1. This person inputs, a set of 2 messages. And this person learns at the end exactly which, it's like a mux. He learns the mux of which message he's indexing. Okay? I'm not going to go any more into how this protocol works. We're going to treat it as a black box. But that basically completes the definition of the protocol. So what happens is, once he gets all of the input keys here, he can follow this circuit up wire by wire and learn the output, and then he can send the result back. So here is basically Yao's protocol. First message, Alice sends over her circuit as well as the keys corresponding to their input. Next, Alice and Bob do this oblivious transfer. And finally, Bob says the answer is 4 or 7, whatever it is. Okay? And this is an honest but curious protocol, and we can actually state and prove the theorem, which is that if encryption and oblivious transfer are secure, then Yao's garbled circuits method is honest but curious secure. Okay? And let's think about how much overhead was added by this process. So the first thing is that we added a few extra rounds. The simple protocol was basically like 1 round, let's say. And here we have to do the circuit thing. We have to do the oblivious transfer. So we added a few rounds there. More importantly than that, though, for every gate of the circuit that we're computing, we add a few encryptions, and for every input, we add one execution of an oblivious transfer protocol. And that's for computation. For communication, we actually have to send the whole circuit, which is not 2 encryptions, but 4 encryptions, right? Conceivably, you might think that you actually need to do 8 encryptions per gate, but actually there's some hacks you can sort of, some nice ideas you can use to reduce the work you do. But still, it's constant number per gate and constant number per input. Okay. So this is kind of the jumping off point, okay? This is considered the small part of the overhead. And it's still a quite open question as to whether you can improve upon this type of thing. Is this overhead fundamental or not? We don't know. And in fact, it's part of this active research program that Steve and I are on. But let me go to basically the result that we do have, which is how to take this honest but curious protocol and make it malicious. And in order to first do that, let's think about what can go wrong, okay? There are 4 spots in this protocol where cheating could happen, right? Alice could cheat in the top, she can cheat in the second thing, Bob can cheat in the second thing, Bob can cheat at the end, okay? You had 3 messages, you make 4 places to cheat, kind of thing, okay? So how can this happen? Well, Alice can send the wrong circuit. She say, you know what? We agreed upon F, but here I'm going to give you a different F. And this F is actually going to reveal all of your inputs to me. Ha! And you won't even know. Okay? Or she could even be more surreptitious about, well, if your input's like this, then it will reveal, otherwise it won't. And so she could play some very tricky games there. Okay? Here's an even more subtle way for her to cheat. So when we're running the oblivious transfer protocol, her input should have been the key for 0 and the key for 1. And here's the trick she plays. She says, actually, I'll put the correct key for 0 as input, and I'll put some junk random key for the second thing. So what happens now? If Bob happens to ask for 0, it works perfectly. He can't tell the difference, anything, nothing goes wrong. If Bob happened to ask for 1, all of a sudden you got a junk value, you got a lemon, okay? And then he tries to run the rest of the protocol and he gets stuck. Now, whatever he does there, he's basically screwed. Because if he goes to Alice and says, oh, something went wrong with this thing, what has he done there?
Confirmed.
Confirmed what?
That he asked for 1.
That he had input 1, right? So Alice immediately learns, aha, so you really thought that thing was worth more than $1 million. This could just be the first bid of his bid or something, right? So sorry, I was running Windows Vista, this thing is like really bad, let me start again. And they run it again, all of a sudden she knows something, right? So this is really bad. This selective failure attack is extremely subtle because it only comes into play when, when something happens, in some situation, right? Okay. Of course, Bob could cheat on this OT and get both keys, and all of a sudden, and so forth. He could also cheat, send the wrong answer, but there's some other simple ways to get around that. These 3 things that I've just discussed, these are the critical places where this thing breaks down, okay? And so this step of going from honest but curious to fully secure, it was first solved, it was, basically a classic problem. It was solved in 1986 by, Goldwasser, Goldreich, Macaulay, Victorson. And it was basically, this paper introduced generic zero-knowledge proofs, okay? And so what you're going to do is prove that at every step of the computation, you're following the honest instructions. This is called the commit and prove methodology. And it's highly compelling because it's very generic and sort of easy to really comprehend as to what's going on. You just prove that you're doing the right thing. And you can do that because this result says you can prove anything in zero knowledge. Any statement, any theorem that's in NP, you can prove in zero knowledge. And so that you could do here. The problem is that this transformation has incredible overhead. Many, many rounds, I estimate around 18, which is really not that bad. But this is the big spot here, okay? However much time it takes to make one encryption, all of a sudden that factor becomes a part of the overhead. So if it took like 10,000 cycles to encrypt something, right? This generic zero knowledge technique is going to basically take, that computation and turn it into a tableau, basically, like it's going to be running the Cook-Levin reduction. So it's going to be looking at the Turing machine, which implements that, and looking at the tableau of that, turning that into an instance of 3 coloring, and then running a protocol on that. Okay, and so the overhead that you have is enormous, to the extent that nobody in the last 25 years has ever attempted to implement this type of thing, because immediately the thought experiment becomes too overwhelming that this would never work out. Now maybe there's some really good, deep ideas, fundamental ideas that get around these bottlenecks. People think about this all the time. And in fact, there have been some recent improvements in the last few years, but still nothing that leads us to believe that this would be a good way to actually implement this in practice. Better as a philosophical statement of possibility, but and feasibility, but not as something reasonable. So that brings us finally to this statement of the work that I'm working on. And there's some technical aspects of it which I don't want to get into. What I want to do is give the high level view, which is that we're going to use these, we're basically doing this hybrid method. It's a classic trick in algorithms and everywhere else. You take what's good from over here and good from over here, and you compose them in a nice way so you get the goodness over here and the goodness over there, and the penalty is actually not low. Anybody in algorithms know this is kind of a bread and butter technique of recursion and sort of like divide and conquer, and all of these type of ideas. Advanced ideas actually are using this type of thing that if you compose things, sometimes you can get the best of both worlds. And so here's the idea. Okay, so instead of just running one version of this protocol, of the honest but curious protocol, right? Because if we just do one, then Alice can basically cheat on this circuit, and I would have no idea. The simple idea of cut and choose is basically, let's consider the first message. Alice sends 100 copies. She makes 100 copies of the circuit. Okay? And she sends 100 copies over. And then we do 100 OTs to get the keys that I actually need. Okay? And now, if Alice was cheating on any one of those, here's what I do. I say, you've sent me 100 circuits, and I trust you. I think you're a very honorable person. But just to be sure, how about I just pick these random subset of these things? How about instead of actually using this circuit to do any computation, you just reveal exactly how you produced it. Just give me all of the keys for 0 and 1 and so on and so forth that you used for creating that circuit, and also for running the OT protocol. So there's some slight changes to the OT protocol that we make that allow this type of thing to happen. But essentially, Alice sends this 100 times. Bob basically says, reveal all of the inputs that were used to make these particular randomly selected subset of these things. Okay? And now what can we conclude? Let's say we open up half of the circuits there, okay? We can conclude that with very high probability, the majority of the circuits that are left over are actually good ones, right? So if Alice, let's say there were 100 and I opened 50 of them, right? Now suppose Alice actually, made 51 bad circuits, more than 50 bad circuits, okay? Then essentially she's always going to get caught, because I picked 50 of them, 51 of them are bad, one of them is going to be bad for sure. So she has to make less than 50 bad ones. Once she makes less than 50 bad ones, right? Now, what's the only way that I could pick all of the good ones and have the rest of them all bad? There's only one way for that to happen, and there's n choose n over 2 type of different other ways to do it, right? So if you do the calculation, it's very high probability that you do this. Now, actually, you can do some more hard work, and sort of, some more sort of detailed analysis of this type of thing. And actually, if you open 60% of the circuits and evaluate 40% of them, that optimizes the probability. And that's kind of one of the nice little cute contributions of this, just doing that analysis nobody had done. And it turns out that there's a slight optimization that we can do there. Yeah?
Are the circuits identical?
No. So each of these circuits, she computes them completely afresh. She just runs the same process over and over.
It has to be.
It has to be, because otherwise, then the unopened ones would be exactly the same as that, and then you'd learn them, right? So it was as if she's running this protocol 100 times, and then half of them just have to be completely revealed to indicate that yes, in fact, with high probability, I actually followed the procedure properly. Unfortunately, okay, so at this point, now notice Bob doesn't have Alice's keys, so we have to modify the protocol so that at the end of this process, after the ones are opened, right, Alice sends over the copies of her input keys that corresponded to the unopened circuits. But just making this small change, unfortunately, it opens up another can of worms. It creates another way for Alice to cheat. What could she do? Aha! I've sent you 100 circuits. You've opened 50 of them. Very nice. Now, here are my inputs to these 50 circuits. I'm an honorable person. I was honorable yesterday, so today I'm certainly an honorable person. Here are my inputs. What could she do? Yeah. So the new problem is that over here she could be saying input 001. Over here she could have a different input. Over here she could have yet another input. Okay? Her inputs might not be consistent, and you might think that this is not a worry, but actually, if depending on we want to do this for NEF, and so you could basically find examples where if this, there are concrete examples here. You can talk to me later of how Alice can basically learn information about Bob, if this type of attack is allowed. Okay, and basically the situation becomes if she puts different inputs here, Bob is going to basically find different outputs possibly. Okay. And it could be the same sort of selective attack. In some cases, there won't be different outputs, but in some cases, there will be different outputs. And so depending on what he does, you'll basically learn something from that situation. So what we have to do is a consistency check, okay? And there are two nice observations about this consistency check. First thing, it's a smaller problem than checking if a circuit is consistent. This is a huge thing. This we're only checking about input consistency. And the second really important thing that makes our work special is that we've discovered that we can use a weaker type of proof for this type of consistency check. And, like many of the things Steve and I work on are like finding the weakest assumption for encryption. Like, for example, I think he gave a talk on this one-bit encryption thing. Like, can you build a big encryption scheme using a weaker one-bit encryption scheme? Yes, you can. But it turns out that construction wasn't necessarily more efficient than just the ones we know. In this case, using a weaker proof actually works out in that the weaker proof actually has a more efficient implementation than the currently known ones. Okay, so intuitively, it's a smaller problem to check these type of things, and you can use weaker proofs, and so it becomes much more efficient. And that leads us to basically, a survey of what our basic result is. Other people have other suggestions for this type of thing. The big things are. For all of these type of works, we basically go from ns squared to ns, okay, and that's a nice improvement. With this work, LP10, they took a very similar. They had the same idea in mind, and asymptotically, our results are very similar. But we have theoreticians ignore constant factors, but in our case, our constant factors are better. Our protocol has a significant improvement when you're talking about two outputs. So what do I mean by two outputs? It's conceivable that Alice wants to learn function f1 of xy, and Bob wants to learn function f2 of xy. Okay? And that's called the two-output case, and our work in there is significantly better than everybody else's. And the other really big important thing about this is that our protocol was so conceptually simple that we could actually implement ours, and we did. And here are some running times. You can ignore all the other we did two experiments here. Like this one is basically like a dot product and millionaires type of problem for the two output case, F1, F2. This one is basically AES. So player 1 has an input key. Player 2 has the actual Y, and what player 2 wants to learn is the evaluation of Y on AES of X. Okay, and this gives you an idea of the number of gates involved in the circuit. So 33,000 gates, roughly. Another optimization I didn't talk about is you only have to do work for the gates that are not XOR gates. And so, we have this many gates, roughly 12,000, and these are the running times. The previous approach took basically 900 seconds, and our thing takes like 260 seconds, which is still a lot of work.
What's on slower versus on fast?
In order to really compare with their work, so the protocol is LPO7, the implementation is this right here, and they ran on some crazy machine. They run on some machine. And of course, these things are so hard. This is why the referees asked us to make this table. It's very hard to compare my machine versus your operating system. And so we tried to get the closest one to theirs, and it was a slower machine. The faster machine basically gives the same thing. And the important thing here is communication is also the important factor. We have much smaller communication, which is what the, which is what the dominant factor, like, exchanging information over the internet type of thing is that there. And here's some other type of thing. The point of this table is to show really where all the time is being spent. Circuit construction and cut and choose type of, that's kind of where the effort is. And this basically gives us where the bottlenecks are. Okay, and it leads to the next type of, the next improvements we want to do. We have ideas. The first 20x improvement is actually quite easy. Having implemented this, you can easily pinpoint the spots. It takes time to implement those things, but there's some fundamental things you can do that are faster, and then there's some engineering things you can do, and both of those things basically give you the first 20x, right? So I think these things can basically be from 260 seconds. I think it'd be less than 10 seconds, no problem. The next 20x improvement, that's where the real the real trouble is. You basically have to come across this. You have to find better ways of doing these type of things here. Okay. I was going to run a demo to show you this, but it actually takes 4 minutes. So, and I don't have it set up here on this laptop. So in the last 15 minutes, a question?
I had a question. So I don't know if you're going to talk about this, but what about the case where in the end Bob can lie about what the circuit evaluation?
Yeah. So there's
run this. Does Bob just run the same protocol but from the opposite perspective?
Could be done that way, but there's actually a better way to do it. When Alice makes the circuit, instead of just putting 0, she puts 0, a signature of 0 in there. And so Bob has to send back, the answer was 0 plus here's a signature of it, so he can't lie about it. And signatures are hard to forge and so forth. So that part's the easiest part to fix of this thing. That's why I didn't sort of talk about it. What I want to spend the next 15 minutes doing is basically this project that Steve and I are working on. It came from this observation that these two things are really, the tough part. And so let's consider what are the fundamental limits. And one of the fundamental limits of this entire Yao method is that the communication has to include order the size of the circuit times some security parameter, like I said, 100. Right? That's a really big bottleneck in this thing. The communication and therefore the computation are proportional to the size of the circuit that you're evaluating. And the question that we asked is this a fundamental bottleneck or not? Okay? Can you get around this using some other technique, some other trade-off perhaps? And that's where this, these two big ideas came in this idea. The first big idea is we go directly from the simple protocol to a fully secure protocol. We skip the layover in Detroit. Okay, and this approach basically gets us across this boundary. And now let me basically give you some highlights of how this idea works. Okay, so the plus of this protocol is that the communication is now basically the number of inputs times a security parameter to some C. This C is undetermined. It's, in flux, but it's some constant. We hope that it's 3. Right now we think it's 9. Okay? So that's a big, but notice the C is not in there. And that's a big, that's the big leap here. The minus.
Just because that C is not the circuit C.
Oh yeah. This C is a small constant C, not the size of the circuit. Yeah, sorry. The minus of this approach is that it requires an honest majority. So it doesn't work in the two-party case. Okay, you actually need 3 people, and you have to have this trust assumption that a majority of those 3 people are honest. So 2 people are honest, 1 person could be cheating. If you have n people, then n over 2 plus 1 people are honest. So that's a different assumption. And of course it has this large hidden constant. I'll tell you more about it on the last slide as to sort of where the trade-off actually works and why we haven't yet implemented this thing yet. Here's a high-level idea of the 2 big things that we've come up with. Lots of adjectives here. It's an encryption scheme. We have a new encryption scheme. We are sort of we love working on encryption. That's most of our work, together is about encryption. So we have a new one. It's fully homomorphic. I'll explain what that means in a second. We use ideas from other people for making it fully homomorphic. The third idea is ours. It's a threshold system. So what that means is essentially, we can take the secret key and split it among each of us. If there are 50 people in this room, we can give everybody a little piece of that key. And the property is such that if you just have the little piece of key, you don't learn anything. If k people have that little piece of key, they still don't learn anything. If k plus 1 people have that little piece of key, they can come together and actually decrypt the ciphertext. That's the threshold property that we achieve. So that's idea 1 in this paper. Idea 2 is we have this new black box way of making a proof of knowledge about an encryption. So it's a method of saying, here's an encryption, and let me prove to you that I actually know what's inside this encryption. And you can, of course, do that using generic GMW techniques, but we saw how those things work. We actually come up with this nice, efficient new idea for this. And those are the 2 big ideas. So what does homomorphic encryption allow you to do? If you're given a ciphertext for message 1 and a ciphertext for message 2, you can apply this process, here depicted by this brown arrow, that allows you to compute an encryption of G of M1 and M2, where G is either plus or times. So you have you have the ability to by yourself do a little bit of secure collaboration non-interactively. Okay? And then basically the idea is you can repeat this to compute any circuit that you want to do. So let me give you a brief idea in the last few minutes about how this works. So the setup is that there's a public key for this threshold fully homomorphic encryption scheme. Everybody has the public key, and everybody has a piece of that secret key. Okay? And now, in the first step, we all go and we encrypt our input. Our player 1's input is x1, player 2's input is x2, ... So everybody just broadcasts an encryption of their input. Okay? And then we have this circuit that we want to evaluate. Before, we would have sent these garbled tables corresponding to each of these gates. Now that we have a fully homomorphic encryption scheme, we just use the homomorphic part to evaluate this. So each AND gate, or each AND and ORs and so forth, can be turned into pluses and times through some algebraic manipulation. You could believe me there. And then you basically evaluate the circuit from top to bottom. At the end of this process, everybody will hold an encryption of the output. And now we use the threshold decryption process, okay, where if a majority of these people are honest, they can all come together, bring their little secret shares, and the majority can recover the output of this type of output, okay? And so those are like basically the steps. Now the thing is, there's one part of this protocol that's completely broken. Sounds like a very good story, but it's broken. What is it? How can someone cheat in this situation? And the hint is, remember, we came up with 2 little objects there. So that should come into play as to what someone can do to cheat here.
Can you repeat the slide on the objects?
Ah, yes. Okay, so it's the proof of knowledge are the 2 objects we have here. And this is where this thing comes in. But that's kind of a technical way to solve the problem. But here's the way that someone cheats, okay? Aha. So I'll illustrate it with an example. What's your favorite movie? I'll tell you mine after you tell me yours.
The Social Network.
I love The Social Network. Yes, Mark Zuckerberg and Jesse, they should have won the Oscar, right? So the point is, I've ingratiated myself with you by claiming to know the exact same network. If I would have answered the question before, obviously I would have had a small chance. I could have picked the Black Swan, I could have picked the other one, So the point is, what can happen here is that player 2 cheats. Player 1 announces the encryption of his input, and then player 2 says, what a coincidence. That's my input too. And you might think that this doesn't really have a big effect, but suppose we're in an auction and we are all, bidding for the red violin, that one really great Stradivarius thing that's like has the beautiful sound and the history of all and so forth, right? Okay, so the great violinist over there decides to put his bid in. Steve, go ahead, encrypt your, send your encryption of the bid. Done. Okay, I take that and it's a very good coincidence. I had exactly the same bid as you. Amazing that we picked the same thing. And now all of a sudden, I'm in a contention, I'm in a runoff. If he's going to win it, I have 50% chance of winning it as well, assuming that they do like a coin toss to break ties or something like that, right? So this is a very bad way to cheat in a protocol. If I'm able to, without knowing what your input is, basically copy your input to any protocol, this is a very bad thing. And this scheme naturally allows that type of thing, because we're using this homomorphic encryption and type of thing.
I just add 1 to my bit.
What?
I just add 1 to my bit.
And in fact, it's malleable. So you can add 1 to your bit. Always beat him, right? Always beat the guy that would have won the red violin. So what we do to fix this thing is use our second component. We actually say, you have to give an encryption of your input, and you have to prove that you know what's inside the input. And for technical reasons, this actually eliminates this type of way of cheating and every other way of cheating. And so that's where the second component comes in. So these are the things that we've produced. These are the new objects that are in that paper. Okay, and I'm not going to give you the threshold setup and the threshold decryption. I'm going to skip over the technical details of how we do that. But that's kind of how we make the whole thing work. But the bad news, this is the part I want to focus on. So this approach is good in the sense that it eliminates that order C, okay? But these two people, Gentry and Halevi, Gentry is the one who is like principally responsible for the fully homomorphic encryption schemes. They implemented it. They're very good implementers. And they wrote the time to run one bootstrapping operation. So one operation, like one homomorphic gate essentially, on a good CPU. They're at IBM, so they are not poor for big computers. Ranges from 30 seconds for a small toy setting, which can easily be broken, to 30 minutes for a very good security parameter. Okay, so as I said, that C is unknown, but just doing one of those operations takes 30 seconds to 30 minutes. And now let's go back to our table here of how many operations we had to do. 10,000. Okay, so as it currently stands, our protocol has really good benefit in that the communication is independent of the size of the circuit. But the computation is where we paid for it today. Because obviously, this takes 260 seconds, and I said I can, based on the insights we have, make this 5 seconds, okay? All of a sudden, 30 seconds times each of these things is going to be millennia, or not millennia, but 300,000 seconds, or roughly 4 years. Is that right? 86,000 seconds in a day. 5 days? Okay, 5 days.
2,000 seconds is on the order of 4 or 5 days.
Yeah, 30 minutes. Okay, yeah.
30 minutes
Yeah,
would be
yeah.
much longer.
Yeah, okay. So that brings me to the end of my talk, which is that, hopefully I've given you some indication of the two types of, we have many other projects in play right now, but they're all driven by this fundamental observation of what are the limits of these type of process of making secure protocols. Can we get around, can we actually come up with ways which eliminate the extra communication, the extra computation, reduce the number of rounds, and so on and so forth. And so with that, I basically, maybe we should ask the people if they have any questions.
Indianapolis, do you have questions?
No, we don't. Thank you.
So until homomorphic encryption becomes efficient, it's no use doing the optimizations you're doing?
Well, no, because we're hopefully, this black box proof of knowledge, which was, motivated by this application, that can actually work in many other protocols too, because other protocols need this type of proof of knowledge thing for these type of similar things. And so it doesn't work in our two-party thing. We actually have something simpler and faster there. But, those ideas actually, there's some good ideas that we're going to apply other places. In fact, we already have some approaches that...
I had a question about the black box knowledge kind of gadget that you're using. Is there ever a black box for ignorance? Because what you really want is for somebody to prove that they don't know something.
What do you mean?
Well, what you'd like to do in the Austin case is you'd like the second person to prove that they don't know.
So
to
typically...
to prove that you're not copying something, you should prove that you don't know what you just heard, or the unencrypted version.
So, exactly. The way that you achieve this I don't know type of thing is two parts. The encryption typically should give you this the security property of encryption is, if I give you encryption of a 0 versus a 1, you are completely unable to distinguish between what I gave you. That's kind of the property of encryption. And so the only thing you really could do is copy or maul this type of thing. And so the way you get around that, the only known ways we know how to do that are basically through this proof of knowledge. So I could have given you an encryption. The property of encryption by itself tells you that you shouldn't be able to tell whether it's a 0 or 1. And the only thing you could do, perhaps, is manipulate this object, give it back to me, and just you've manipulated it in some way that you've changed it, you've added one to it without knowing what's in there, or you've squared it or something without knowing what's in there. And the only way that we can prevent that type of thing that we know is this type of proof of knowledge type of thing. I mean, there are some other ways, I guess. Another approach is to make a scheme in which it's impossible, so we can prove that in addition to your ability of not knowing whether it's a 0 or 1, we actually show that it's impossible to manipulate it. And in fact, that was a core piece of the 1-bit to many bit paper that Steve and I did. How to make that was a core step that we had in there. But that wouldn't be useful here because principally we want the encryption scheme to be fully homomorphic. We want to give the ability for someone to take an encryption and manipulate it. So the only way that we are able to conceive of this is to introduce this proof of knowledge and come up with the fast one. And by black box, what I mean there is that the only operations that you have to run to produce this thing are to run the encryption itself. Okay? You just have to run the encryption a few times, just like this sort of copying it S times thing. It's a similar idea there. And it's much more efficient than any other zero knowledge techniques that we know for this type of encryption scheme.
Maybe, Larry, one of the things, I don't know if you're familiar with the definition of proof of knowledge versus just the general proof, but it basically means if I convince you, not only that I convince you that the statement's true, but that I actually know why the statement is true. Right. So
Yeah.
I have, in essence, a witness that I like.
Right.
Yeah.
So you couldn't really hope to do that for ignorance.
Yeah, in general, I mean, from a computer science point of view, we think of it as co-NP. Like you can't,
Yeah.
It comes down to the difference between proving I have $1 million versus proving I don't have $1 million. It's easy to prove I have $1 million. I just show you my bank account statement. It's very
The
hard for me
IRS
to
would love
prove
for
to you that I don't have $1 million because you check all banks, you check under my bed, you check in my sofa. Right?
Yeah. Or I've heard the better version of that is to prove that you don't have a sister, right? So. Any more questions?
When in the first protocol you said, for example, Alice can send 100 messages or circuits to Bob, and then there was a cheating that the keys can be not consistent.
Yeah.
My question is, these circuits are different, so the keys must be different. Why this can be happen?
Very good question. So the circuits are different, as you said. The keys for them are also different. And so what I mean by consistency is that the key that I give you for this circuit, it corresponds to a 0. The key that I give you for the next version of the circuit, for the same wire, although it's going to be syntactically different, this one's going to be 10110, this one's going to be 00111001, they both correspond semantically to the 0 wire. The consistency check is to make sure that those keys, all of the keys that you give me for the first wire, they all are keys that correspond to the same 0 wire. That's the check that needs to be made there. Good point.
Did you talk about, I can't remember, about checking the consistency of the circuits, or that was the whole point of the current use protocol, to make sure that all the circuits were constructed in the same way. So that's the part where you check that Alice is not creating different circuits.
Exactly,
okay.
exactly. Because we've agreed upon a circuit, and we open half of them. And as you open them, I can check that this gate isn't in fact an AND gate, it's supposed to be an AND gate, it's an AND gate,
Right.
and so on and so forth.
I'm trying to think if like the Monty Hall problem fits in here somehow, but I don't think so. Is like when you factor, I guess the Monty Hall problem is more like if Alice herself said,
Yeah.
okay, I'm going to open up.
Yeah, I'm going to open a good one up for you. Yeah,
Right, but
this is
that
a
doesn't
great
apply
example
to
of demonstrating. It's like, I have good ones and perhaps a bad one. So you open one, suppose it's good, and then Monty Hall says, let me make it better to prove to you that it's a good one. Here's another good one. Would you like to, and so forth. Yeah, it's a good point. It's a good point of proving how that, of introducing the Monty Hall problem. But here we get around it with a much simpler analysis. We just say, I give you 50, S or 100, let's say, and you pick half of them or 60% of them, and with high probability, at least the majority of the rest of them are good ones. And if the majority is good, then this guy can evaluate all of them and then take the majority of the output and so forth. Well, if there are no other questions, thank you very much for your audience. Again, thank you for the center for inviting me. I have an excellent time coming here and collaborating, and very, very happy to visit. So.